Hey everyone, welcome back to section 3.3, and now I'll be going over complex valued functions and Euler's formula. So let's just begin with the form of the root, which is going to be in the form a plus or minus bi, where I is equal to the square root of -1. And just plugging this into like the exponential form of it, it's going to be e to the a plus bi times the quantity times like x. And then from this, we will move into like Taylor-Maclaurin series. So if you guys remember back to Calc BC, the Maclaurin series for e to the t is equal to the sum from n equals 0 to infinity of t to the n over n factorial. So that's going to be equal to 1 plus t squared over 2 factorial plus t cubed over 3 factorial plus t to the 4 over 4 factorial. And then it's just going to continue on. So if we sub in I theta for t, so we get the e to the I theta is equal to the sum of n equals 0 to infinity of I theta to the n over n factorial. Evaluating this, we get that it is equal to 1 plus I theta minus theta squared over 2 factorial minus I theta cubed over 3 factorial plus theta to the 4 over 4 factorial plus I theta to the 5th over 5 factorial, continuing. So from this, we can get, you can just break this up into I and non-I components. So that's going to be 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial, continuing along, plus I times quantity theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, continuing. So if you guys remember back to Calc BC, these two sets of infinite numbers is similar to what we knew before. And if it does look familiar, it's because it is. The left side is actually equal to the Maclaurin series for cosine theta, and the right is, I'm sure as you can guess, is equal to sine theta. So if we plug this back in, we get that e to the I theta is equal to cosine theta plus I sine theta. This is going to be known as Euler's formula. Just remember this, because we will be using it a lot in the rest of this lesson. So now we're just going to define a function e to the z, where z is equal to x plus iy. And so e to the z is equal to e to the x plus iy, which is equal to e to the x times e to the iy. And then right here, already applying Euler's formula, we're going to is equal to e to the x times cosine y plus I sine y. So from this, we are going to define the complex valued function f of x, and that is going to be equal to small f of x plus I times g of x. And so the small f of x in this case is going to be known as the real component, and the g of x is going to be known as the imaginary component. So both of these are still differentiable with respect to x, so as is the whole complex valued function. So big f prime of x is equal to f prime of x plus I times g prime of x. So from this, we're going to just define big f of x as e to the rx, where r equals a plus or minus bi, which remember is the form of the complex root. And then we are going to just plug it in here. So e to the a plus bi times x is equal to e to the ax times cosine bx plus I sine bx. Notice again, we are applying Euler's formula. And then to account for the case of the negative, we are going to go with e to the a minus bi times x is equal to e to the ax times the quantity cosine bx minus I sine bx. So from this, I want you guys to note that the derivative of e to the rx with respect to x will be re times e to the rx. And with this, I want you guys to just remember this. If you want the proof, you can go on into the book and read it for yourself. From here, I will be moving into the complex roots theorem, which is also known as Theorem 3. So if the characteristic equation that we defined above is a sub n r to the n plus a sub n minus 1 r to the n minus 1, continuing until a sub 2 r squared plus a sub 1 r plus r naught is equal to 0. Has an unrepeated pair of complex conjugated roots a plus or minus bi, where b is not equal to 0, then corresponding part of a general solution of a sub n times the nth derivative of y plus a sub n minus 1 times the n minus 1th derivative of y, continuing until we get to a sub 2 times the second derivative of y plus a sub 1 times the first derivative of y plus a sub 0 times y is equal to 0, has the form e to the ax times the quantity c1 cosine bx plus c2 sine bx. From here, we're going to go into an example. So find the particular solution of y double prime minus 6y prime plus 10y equals 0 with the initial conditions y of 0 equals 3 and y prime of 0 equals 6. So right now would be a good time to pause and work through the example by yourself. And now I'll go through it. So here we'll just substitute in r for y. So we get here r squared minus 6r plus 10 equals 0. In this next step, we will be completing the square. So r minus 3 quantity squared plus 1 equals 0. And then doing some basic algebra, we get that r equals plus or minus I. So plugging this into the Euler's formula, we get that y of x is equal to e to the 3x times the quantity c1 cosine x plus c2 sine x. Now, generally this is just going to be our general solution, but we want the particular solution. So moving, we'll be taking the derivative, so y prime of x is equal to 3 times e to the 3x times the quantity c1 cosine x plus c2 sine x plus e to the 3x times the quantity negative c1 times sine x plus c2 cosine x. So now we are just going to plug in our initial conditions. So in this case, y of 0 equals 3. So y of 0 is equal to e to the 3 times 0 times quantity c1 cosine 0 plus c2 sine 0 equals 3. Simplifying this all down, we get that c1 is equal to 3. And then likewise for y prime, we get y prime of 0 equals 6. So that is equal to 3 times e to the 3 times 0 times the quantity 3 times cosine 0 plus c2 sine 0 plus e to the 3 times 0 times the quantity negative 3 sine 0 plus c2 cosine 0 equals 7. This all simplifies down to 9 plus c2 equals 7. And subtracting c2 or 9 from both sides, we get that c2 equals negative 2. Now we plug this back into our initial general solution, and we get that y of x is equal to e to the 3x times the quantity 3 cosine x minus 2 sine x. So right here, I want everyone to pause and read the little half page of 169 just to understand the next couple steps that we'll be going through. Now welcome back to our video, and now we'll be going over the next example. So find the general solution of y to the fourth derivative of y plus 9y equals 0. Again, not right now will be a good time to pause, and I'll be going through it. So again, we will be going and substituting in r for y in this case. So r to 4 plus 9 is equal to r squared squared minus 3i squared is equal to 0. Now if you notice, this is actually taking the form of the difference of squares. So we're going to split that up, and it's going to be quantity r squared plus 3i times the quantity r squared minus 3i. Doing some basic algebra, we find that r is equal to plus or minus the square root of plus or minus 3i. So this is the point that I wanted you guys to get from reading page 169, and that is I is equal to e to the I pi over 2, and negative I is equal to e to the I 3/2 pi. So from this, we get that square root of 3i is equal to the quantity 3 times e to the I pi over 2 to the 1/2 is equal to the square root of 3 times e to the I pi over 4. Applying Euler's formula, we get that square root of 3 is equal to cosine pi over 4 plus I sine pi over 4. Evaluating cosine and sine, we get that it is equal to the square root of 6 over 2 plus the square root of 6 over 2 times I. Now let's apply this to the other case, which is the square root of negative 3i, and we get that it is equal to the quantity 3 times e to the I 3/2 pi to the 1/2 is equal to the square root of 3 times e to the I 3/4 pi. Applying Euler's formula in this case, we will get the square root of 3 is equal to cosine 3/4 pi plus I sine 3/4 pi. Evaluating sine and cosine, we get that it is equal to the negative square root of 6/2 plus the square root of 6/2 times I. Now, plugging all of this into our general solution formula, we'll get that y of x is equal to e square root of 6/2 times x times the quantity c1 cosine square root of 6/2 times x plus c sine square root of 6/2 times x plus e to the negative square root of 6/2 times x times the quantity c3 cosine square root of 6/2 plus times x plus c4 sine square root of 6/2 times x. Next, we'll be moving into the repeated complex roots. So, for repeated complex roots, theorem 2 holds true. That is, a conjugate pair, a plus or minus bi, has multiplicity c, then the corresponding part of the general solution has form a sub 1 plus a sub 2x, continuing until a sub k times x to the k minus 1 times e to the a plus bi times x plus b sub 1 plus b sub 2 times x, continuing until b sub k times k x to the k minus 1 times e to the a minus bi times x is equal to the sum as p goes from 0 to k minus 1 of x to the p times e to the ax times the quantity c sub p cosine bx plus d sub p sine bx. Additionally, it can be shown that the 2k functions x to the p times e to the ax cosine bx, x to the p e to the ax sine x, as p goes from 0 to k minus 1, in the equation above are linearly independent. So now we'll be moving into an example. So find the general solution of d squared plus 40 plus 5 quantity squared times y equals 0. Again, now will be a good time to pause, and I'll be going through it. So again, we are just substituting r in, but in this case, instead of for y, we'll be substituting it in for t. So r squared plus 4r plus 5 quantity squared is equal to 0. And we're going to complete the square here, so r plus 2 squared plus 1 is all equal to 0. Doing some basic algebra, we find that r is equal to negative 2 plus or minus I with multiplicity 2. Now, we can just plug this in and find that our general solution is y of x is equal to e to the negative 2x times the quantity c1 cosine x plus d1 sine x plus x times e to the negative 2x times quantity c2 cosine x plus d2 sine x. And that is it for our lesson. I hope everyone enjoyed, and have a nice day.